And so we're looking for entrepreneurs. So if you want to start a company in the big data space around application data science, talk to me after. A little bit about me. This is two-time world champion of beard and title. I'm sort of potentially good in the beard, still in training. You is my enemy. This talk basically covers a book they wrote called Agile Data Science. You can get it from O'Reilly, where I get the most royalties. Using the code off-D. Amazon really is not great for authors. So we go kind of fast, but don't worry, there are numerous blog posts that sort of cover all this if you look at my name, and if it's not in the blog post, it's in the book. So Agile application development for web applitions is a pretty mature field of endeavor. And so you can set out to build a web application using an Agile process and a post-build framework and be pretty sure you're going to arrive at something that's useful to somebody. And then there's data warehousing, which is how people have traditionally done analytics at large companies. But they tend to sort of be fragmented so that not all departments have access to the data that all the departments have. That's kind of a problem. And then there's scientific computing or high-performance computing. Traditionally, this stuff is really neat, but it's been incredibly hard to use. Like, I tried to do MPI, but it was really hard. Like, I couldn't pull it off. I was not able to use it after MPI in college. I played around with it. But you might define data science as the intersection of these three fields. And so now we've got these data centers as computers. We have warehouse scale machines, again, just like old Univac, that kind of thing. But because of discrepancies between latency, bandwidth, and capacity of RAM, local disk, and network, it's actually very difficult to use commodity hardware to build a large warehouse scale computer that works. So it's a very difficult endeavor. So like Hadoop to the rescue. It's sort of a high-performance computing system that is actually very easy to use. There are tools like PA, Hive, and Cascade that let you write MapReduce jobs without thinking in MapReduce. The main benefit of Hadoop is that it's just incredibly cheap to store all your data. That's kind of where the big data trend came from, looking to local disks to make storage very cheap. So what that means is a department head can buy a Hadoop cluster on their credit card to get started. Once that happens, the data silos sort of come crashing down. Everyone ETLs data in to this data lake thing, and you start doing joining you've never done before. It's a very exciting time. But like now what? You've got this Hadoop cluster. What new opportunities does it enable? So I think the answer is the analytics applications, applications that seek to give answers to tough questions or to predict the future. The thing though is from customer through marketers and business people, product managers, designers, developers, and researchers, nobody actually has all the skills required to make an analytics application, and so it's an inherently collaborative effort. So it's best attacked with a small team of generalists. The fewer people with the broader skills, the better. Because when you get too many people, you get a lot of transactional overhead. That doesn't mean large organizations can't have expert researchers. They just tend to share a little bit of their time aside from their research when they expertise between the model. So the goal with an analytics product is to get insight into the product. So how do you do that? The back end has now gotten much thicker, and we're doing research on a Hadoop cluster that can take 10 to 100 times the amount of time it would take to sort of scan the results of the process in an application. So there's this application development versus research time like disjoint. That's sort of a great problem in the field. And most of seeks to address that. So the question is, how do you ship insights efficiently? Very common story in the industry for research to never really hit the market. And so we don't want that. There's definitely a wrong way to go about this. And it starts with, hey, we made this great design, good job with the future for it. So our data scientists. And then inevitably, hey, what's taking you so long to reliably predict the future? And then you make a prediction, but the users don't understand what 86% true is. I don't know if you ever use Flightcaster, but my flight's always 86% on time. I kind of know what that means, but like my mom doesn't get it at all. So presenting predictions can be really tough. So you're freaking out, and the plane is crashing into the mountain. That's an Airbus, not a phone. Does anyone know what plane it really is? I don't actually know. Cool. So what's that? Timeline disjoint, though, reminds me of it's like the waterfall method of software engineering, where you're sort of starved for data. So you end up going back to like gathering requirements, doing the design, then doing the implementation of that design, and getting back to sort of see if you've achieved anything with verification. But by the time that happens, like the requirements have changed, and you enter this like cycle of woe that software development used to be before Agile processes came about. And so there's this chief problem when you try to sort of productize insight that you can't really design insight. You have to discover it. And you discover things by exploring. And so a data science team should make its primary activity exploration. And so you might formulate a strategy to build an application for exploring your data set, to iterate and publish intermediate results, which become the palette for what you ship, whether that's an application or a system or something. And so there's this idea of data design where the data does the talking. So it's like, it's never the first query or the 15th that gets you insight, it's the 150th, at 2 a.m., that kind of thing. You really want to capture those aha moments where people suddenly glean insight from data as you present things to them. It's pretty slow to do those in batch, and even if you could have an instant SQL prompt, people don't really contextualize data as SQL prompt as well as they would in an application with more context to it. So you can't redesign charts, they end up horrible, they go below the page fold. And if you're doing research to solve hard problems, it's really easy to sort of misdefine the problem so that the researcher will achieve success, but you'll never get any value from the research. I've seen this happen a lot. And as we said, the semantics of presenting predictions are complex. But so the chief opportunity lies at the intersection of data and design. So, okay, how do we get back to agility? So a statement of principles and then tricks to code. We want to set up an environment where insights are repeatedly reproduced and where they're shared with the entire team from day zero, that the application is interactive immediately on raw data. We want our data model to be consistent end to end. So like no ORM, we just sort of want to deal with documents and process those stepwise. We want minimal impedance between the layers of our stack so that it's like a one-liner to go from one level to another. And we mine data, and the scope and depth of our insights grow until they hopefully pay for the application. So this is the sort of snowballing audience Agile chart. The key thing is that the researcher needs to share with the entire team at least weekly. This is sort of counter-intuitive to a lot of researchers who are used to sort of keeping something secret for like several years and then writing a dissertation and getting a prize at the end. So in the system, we value the document over the relation. This is an email I sent to my dad about planting a cover crop in our terrible soil in Georgia. And so the actual raw data for that email looks pretty much like the original.
On the other hand, this is the Enron email set out of Berkeley, and this is a relational schema that represents it. And if you're thinking in this perspective, you're sort of skewed in your thinking. And so I would suggest that relational data is a legacy format. Why join when storage is fundamentally cheap? You can project. You can sort of do far fewer joins in a Hadoop-centric workflow. But also new column compressed document formats like ORC and the Cloudera one. They sort of do tricks so that you can think like documents, but it will store it as a more efficient structure. So we value imperative tools over declarative tools. In data science, you often have data and you're sort of cleaning it up iteratively, you're munging, where you spend most of your time. And so you don't really know what you want to select often. And so imperative tools are optimized for a process. So here's an example data flow. Here's a bigger one. So I like Pig over Hive for doing this kind of work. Pig will eat anything, any data, it can consume it in one way or another. It's optimized, as I said, as an imperative tool for refining data as opposed to consuming it, which is where SQL shines. Pig is imperative and iterative. It's data flows and it's SQL-ish, so if you know SQL, you can certainly understand it quickly, but it isn't quite SQL. Illustrate is a really cool tool that generates sample data based on the actual data, but also it creates example data to satisfy the conditionals of your query. So if you have like x less than 5, it'll show 6 and 4 and 4 getting through. So it's really neat. It helps you to iteratively develop without actually running your whole job on the cluster. You can extend Pig in many ways, use it with external tools. The idea, though, here is to prepare their data as it will actually appear in our app. So there's a requirement, localhost versus petabyte scale, same tools. This is a ridiculous requirement, but with Pig local mode, it's absolutely achievable. You can run on a sample locally. Because we're using document format, it's very easy to prepare a sample, whereas with relational data, you can sort of mess up and none of the keys on the joins will match, and it's kind of a pain. So the idea, though, is that everything, we refine data and then we publish it, and so everything we publish is sort of recreatable from the base data. So I'll talk about MongoDB in a little while. You can get away with using MongoDB because you're not really doing much in terms of your database. And so there's this concept of the data value pyramid that Pete Warden came up with. We start just sort of plumbing records through. Then we start to refine the data by making charts. Then we start to link things together and link entities and extract them, and we have reports. And then we're like in a position to make predictions. And we make predictions so that we can enable some new kind of action, create some value.
So okay, step 0 or 1, and then publish records on the web. Mean like the base record, so let's see email. There's tons of ways to serialize events, photograph, script, JSON, DSON, sure there's others in there. I use Agile because it keeps the schema on board, which is really great with large files. Often on a Hadoop cluster, you'll find files that you won't know the schema or how it's stored. It can be frustrating when you use someone else's data. So how do we get events? You might create documents via relational ETL. This is the Enron email data. It's a short tick script to convert it into document format. In the book, we download your Gmail inbox, and then we kind of operate on that, so you can see what's insightful. It's your data. And this is the code that does that. It serializes emails from your IMAP connection as Agile. You might ETL log files. But however we do it, we want to plumb atomic events to the browser. This, as I said, is a stack that we use in the book. We collect events, store them on Hadoop, process the data using Pig, publish it to MongoDB using the MongoDB project, and then there's like a Node or a Python or whatever your favorite language is from that. So our cat the average serialized event. This structure looks very much like an email still. Check our data out in Pig, it still looks like an email. Illustrate command I told you about, still looks like an email. Now we'll publish the stuff to our database. Notice database for Mongo. It's really easy to do this. So check the events there, still looks like an email. Publish the events on the web. This is a Sinatra app. It's a really short, simple web application framework. Still looks like an email. And so the idea here is that, as I said, it's a one-liner to go between any layer of the stack. And so some enterprise tools can be very heavyweight. And it can be a lot of pain to go from layer to layer. But you should really demand a stack that is very easy to transition between layers. So it should be one line of code. So what's the point of doing this, of explaining these records? Well, now everyone's working on real data and they're grounded in the same reality. The product managers can often come up with sort of harebrained ideas, but if they're looking at real data from the first day, they'll probably have better ideas. We'll see how dirty your data is. You have a lot of work to do, but you can ship early and often in an agile way. So now we can wrap the raw data in a project called Bootstrap. It's the most popular GitHub project. It's things from Twitter that lets you make an app that's not totally ugly. To me, that was like just the most amazing thing ever. I've built ugly stuff my whole life. Now it's not distractingly ugly. It's kind of plain. So this is the container for Bootstrap. There's some data in it. Here we do a little bit more massaging to email. I don't have to know CSS to do this. It's great. CSS is a conspiracy for designers to build more hours. And so some technologies really do seem to be favored by consultants because they build that way. So we can list links sort of ends, but that just means it's like your inbox, what that looks like. So here we've got that. You click, you play, there's an email. Once you built that list interface, it's a neat trick with Elasticsearch and a project called Underdog. You can make those emails searchable in just a couple lines of code. You do have, like if you're doing this on your own data, as in the book, you can run Elasticsearch locally. Obviously the caveat is you have to have an Elasticsearch cluster big enough to hold your data. So there could be some setup time. But when you're developing, it's really, really quick. It's like a few lines of code, and you can all of a sudden search your stuff. So, okay, the next level, we'll create charts. So here's a data table and a chart showing the time of day that I send emails. So always start with an HTML table because there's probably holes in your data and you've got to fill in zeros where there's no entry, that kind of thing. So it's easy to fix the bug before you're sort of distracted by the pretty stuff. This is done in a library called NVD3, which is based on D3. It's sort of the newest, coolest visualization library that everybody is using. There's a few other ways to make D3 charts without really knowing D3. They're all pretty cool. So when we're making charts, we start to extract entities, people, places, topics, series, group documents by these entities, rank things, count things, publish top ends, time series. Our goal is to just fill a page with charts. So this is the top end of something in Pig, time series in Pig. This is kind of what our stack looks like. And the idea is, so there's Hadoop, and we publish to MongoDB, there's the application server, and
you may have some more real-time system as well. The idea is that anyone can contribute at the level where they're proficient. So somebody might mock a feature in HTML, CSS, somebody else might use Python and Hadoop, somebody else might use JavaScript and Node to build a feature. So you want people unconstrained to sort of contribute new stuff however they're able. But as a principle for scalability, you want to push the processing back towards Hadoop where you know that it will scale horizontally. So this is how you count the number of emails in different languages. Pig, Mongo's JavaScript. Note that MapReduce is really long even in JavaScript. So never write MapReduce if you could help it. So the next level, we start exploring our data with reports. So here we add related email addresses to our page of charts. And so voila, we have kind of a report thing going. And click around and start exploring. So each entity gets its own type of web page. Each unique entity gets its own web page with an ID. We can start to create links between the base documents and these entities. What you're doing is curating interactive ontologies of semi-structured data, which is just a fancy way of saying making indexes. Actually, a really cool way to get users started other than search is to do a tag cloud of the most important tags entities for that user. But there's a trick here. We're kind of in the Wild West and making indexes up on the fly. If you filter the atomic records in two different ways to create two different entities, and then you link between them later, you'll get misses because the key space is different. So you have to go back and do common filters, like try to put your filters of your data and cleaning all in one kind of pipeline and then branch off into your different types, and you'll avoid that headache. So at this point, you can get real users clicking. Maybe it's not the ultimate user of your application, but if your data is at all interesting, somebody out there will click on your charts, or someone in your organization. And they'll give you a great deal of insight, things you didn't know. Sometimes they'll even know how to clean the data or what's wrong in a structural way. And now we're in a position to start thinking about predictions and recommendations. So we've done a lot of preparation. We've extracted entities, their properties and relationships. Our charts show where our signal is rich. We've cleaned our data to make it presentable in the application. The entire team has a rooted understanding of the data, which they got through exploration. So now we can think in different perspectives and do some analysis. You can think in terms of networks. Anything can be made into a network. This is how you create a weighted email network. The more you send, the heavier the edge and pig. This is a visualization of an email network. The blue people reply to each other. The gray people do not. This is actually a terrible network, but always create a network because it'll get your project funded. People love to look at these things. Like this one will be like, oh, is that a heart? Or I don't know. What they seem to communicate best is that data is complicated and there's lots of nuance, and that excites people. So this is a much better example, but even if you got this, go with it. You can do social network analysis, there's page ranking pig, time series and distributions and histograms. There's holes in your data, you can smooth it. Regress to find trends. I spoke in the Netherlands, and a guy was presenting some very complicated algorithmic trading thing, and he had a chart, and it was the Wikipedia chart for regression, which I also had, so I adjusted it. You can do natural language processing, complicated field, but very approachable in simple ways. There's a macro available that makes doing term frequency inverse document frequency like a few lines of code. There's another one for latent rich allocation. It's another technique. This is a simple visualization of the word frequencies in the email I sent my dad. Plant grass being key. It's a word only. So these are the macros I talked about. This is a man called Bayes that was incredibly naive. We can very easily compute conditional probabilities using Pig. So let's look at an example. This is my editor, one of my editors at O'Reilly, and when I type his email address in, Gmail suggests other recipients. So we can reproduce this feature with this code. Step 1, count the number of times I email each person. So I emailed like 28 times. Step 2, then count the number of times I CC people when I email each person, and divide that by the total that I send. And you'll get a probability of inclusion. And so it's like, oh, next step. But actually, that's it. It totally works. We reproduce the feature. So when Google says big data, simple algorithm, they absolutely mean it. So here we've had a prediction to our report. The probability that my wife will reply to one of my emails is 0.93. Funds from the book sale will go to marriage counseling. So the whole point of this then is to enable new actions. So we can do some business analysis. Why doesn't she reply to my emails? We know what time I email and what time she emails, so it's probably best to email her when she emails, because you go to the top of the inbox. I tend to send really long emails. We can check the probability of reply based on length. Usually my Opus emails are just awkwardly sort of not commented on. People reply to the short ones. Is there original content, or am I just forwarding a bill? You can check for that. Could do sentiment analysis, use R or Python, figure out if I'm being rude. This was a deep moment for me. Do I reply to her emails? I don't think I do, actually. And then do I CC my mom? If I CC my mom, there's never a reply. Thanks.